So in the previous section of this talk, we discussed about the physical picture, like why OTOCs, vanishing of OTOCs corresponds to the presence of chaos in the system. Now, in taking the next step in what our project work revolves around, it's very important to understand how these Penrose diagrams work, and since most members were interested to know detail about it, so we'll speak about it in some detail, and let's see how it goes. So I want to talk about Penrose diagrams, and usually when in literature, like when people talk about these Penrose diagrams, of course there are like very beautiful pictures, and you can analyze, like you can just look at things in a more pictorial way, but these Penrose diagrams can be also used to globally extend the space-times. Something that is also I'm going to discuss towards the end, and I think it's going to be really beautiful. This approach is something that is not very much adopted in the literature, so I'll probably go ahead and claim this as a more general.
You're claiming it?
Yeah, because in the literature, like when generally if you talk about Kruskal extension, I'll come to the punchline of this, but like Kruskal extension was totally derived by playing around with the coordinates, and Kruskal stumbled upon coordinates in which he could globally extend the space-time. But we'll see, without having to think about these coordinates, using the Penrose diagrams and gluing various Penrose diagrams, we can globally extend our space-time.
Okay, if you go by history, like if you go by old books, like even in this book by Gravitation, they have Kruskal mentioned, and they don't have mentioned the Penrose diagrams at all. So I think that when it started, like if you go from the historical point of view, Kruskal came first, I think, or is it?
Yeah, because but like his diagram cannot be said as a diagram in the sense like his coordinate systems were such beautiful that you can, if you drew it into a picture, like they would look good.
Okay.
Penrose diagrams are in a very true sense made to be diagrams, like how Feynman diagrams are a very powerful tool to analyze scattering amplitudes in QFT. I think Penrose diagrams are analogous to what Feynman diagrams are to QFT, although Feynman are probably a little more powerful than this. But Penrose diagrams are extremely beautiful, encapsulate all the geometry, and also give example of how beautifully can we even extend this, globally extend the space-time. Okay, so this generally we will draw these Penrose diagrams for spherically symmetric metrics, and of course in our case also we have it because we set b equal to 0, and so we have a spherically symmetric metric because of that. Okay, so the most general form of a spherically symmetric metric can be written as follows. This is of course in b equal to 4.
So you are working with spherical polar coordinates.
Yeah, spherical polar coordinates. This is the spherically symmetric part. Okay, so this is the most general form of the metric for a spherically symmetric space-time. Firstly, the way I'll go about this is, I will not start drawing those pretty Penrose diagrams that people generally see. Like people just generally take an example of a Minkowski space-time or a Schwarzschild space-time, and then they do some coordinate transformations and they get to the. I will start with the most general approach, like how can we think about Penrose diagrams. The basic philosophy is whenever we draw a space-time, let's consider very simple 2D flat space-time, very simple. We have this x, we have this t. Usually, most of the coordinates that we deal with, like the space-times that they deal with, they extend. They have an infinite extension. Like they keep, they run throughout infinity. So the idea of these Penrose diagrams, or there is a more general class of diagrams in GR that we call as the conformal diagrams. The idea is that whatever this space-time is, can I shrink it down to a finite size diagram such that it encapsulates all the geometric properties of the original space-time.
Okay.
That's the whole idea of a Penrose diagram. Can we shrink this infiniteness? Because of course, dealing with, we cannot look at infinities, right? So it would be very nice if we could shrink this all this information into a finite size of a geometrical figure and somehow encapsulate all the geometry.
Is it like scaling?
Yeah, that's why the word conformal.
Oh.
Yeah, it is scaling.
Okay.
Okay, so that's the general idea. We'll see how we'll go about this. I'll give a more general prescription of this. So the procedure for this is to take a general metric, do a certain coordinate transformation. Suppose, okay, one more thing. Whenever we draw these Penrose diagrams, this is a spherically symmetric part, and this part is what we call as a Lorentzian part for obvious reasons. Because this is the part which is compatible with the Lorentzian signature, right? This is a spherically symmetric part. Penrose diagrams are generally used to study the causal structure of the space-time. This spherically symmetric part does not contribute anything to the causal structure. All the causal information is in this part where we have interplay between
Causal structure means it's between the light cones.
Yeah, so, something like that. So like, even if I don't consider this on, even if I consider this or not consider this, the causal structure of my space-time will not change. Like, the geometry, of course, will be affected.
Yeah.
I will give a way of how to encapsulate for this part.
Okay.
But whenever we draw these Penrose diagrams, we only care about the Lorentzian part. It's the Lorentzian part put very nicely into pictures.
Okay.
And I'm not saying that I'll tell away how do we incorporate for this part into the.
So even if we incorporate them, they don't have any.
No, any causal physics going on.
Okay.
It's this part.
So,
And it's obvious as well. All R and T interplays in this part.
Then we are ignoring all the spherically symmetric thing.
Not ignoring. I'll say, like we'll do all the analysis during this part. It's a very smart geometrical thing. Like we'll do all the analysis for this part.
Mm-hmm.
This is a simple two-sphere, like in D equal to 4 dimensions. This is a two-sphere. Okay, I'll make it explicit now only. Suppose whatever we make, Penrose diagram we make, each point inside this Penrose diagram, like if you want to consider a complete 4-dimensional picture, each point in this Penrose diagram is going to be a two-sphere.
Each point is a sphere.
Two-sphere, yeah. This accounts for this, that's it. As simple as that.
So basically you shrink down your sphere to a point.
Yeah, sort of. Yeah, you can think of that because this is not affecting my the way the causally behavior of my space-time.
Okay.
Right. So the general topology of any Penrose diagram is this. The two R come because of this T and R, and this S2 is this
Sphere.
It is a two-dimensional diagram. So, like, what about the rest two dimensions? It is each point you have to interpret as each point is a two-sphere.
Okay, that's when you are working in 4 dimensions.
Yeah, in 4 dimensions, yes. Okay. So I'll go straight into it now. So I'll do a coordinate transformation. T equal to T of x. Sorry. Capital T equal to as a function of small t small x and capital R as a function of small t small x. So this is a two-dimensional part, right? For when the space-time dimension is 4. These transformations are going to be such that my metric, this Lorentz.
The RT is function A of RT, but not function of.
Sorry.
A is function of R and T.
Yes. Generally, in a Schwarzschild.
Then R and T are function of T and X.
Yeah. Like two new coordinates. I'm just replacing R and T with two new coordinates, such that my metric takes what we call as a conformally flat form. I'll explain why conformally flat. This is my conformally flat form.
What's omega here?
Yeah, the omega is a conformal factor. Basically, when you do this coordinate transformation, anything like when you do this coordinate transformation, your dt and dx, like the coefficients of these two should be same, and they should come out and they should look like this.
It's basically
Minus sign, from where the minus sign is coming?
Minus, of course, the Lorentzian compatibility.
because it's Lorentzian.
Lorentzian, like this.
I know, but from the coordinate transformation, where do you get the?
Suppose we have this simple swasher, like.
Like, so you are in the A of RT, there is minus sign.
Yeah, of course. Yeah, that's why I said this is the Lorentzian part. It indeed means there is some minus. Okay, so this is a conformal factor.
Yeah, conformal factor is basically a sort of scaling.
Yeah, and you can see it.
Yeah.
Like I said, all I'm going to care about is this part in the diagram. Of course, this also has a role to play. Like, but if you just take this part off and you take this off, you have a flat space-time
Yeah.
scale.
Scale to some point.
Like
And
what conformal transformation is precisely this. Like if you have some metric, say let's g of x, you conformal scale it with some conformal factor and you get to a new metric. This is exactly that. At least the Lorentzian part,
okay.
which I'm going to care about. So that's why it is called as conformally flat. This is the metric of flat space, 2D flat space, and it is conformally scaled.
Yeah.
Okay.
But you still have that r squared.
Yeah.
And there the omega 2 square is the
The two sphere.
two sphere, and this is different from that omega that you have written there.
Oh, okay.
So
Yeah,
you,
of course.
yeah, notation sometimes, yeah, because omega and omega.
Yeah, but I have a subscript.
Yeah, okay, fine.
Okay. Yeah. So, in general, four-dimensional space-time, you do such a transformation, and this transformation most of the times is going to be very common. Like I'll come to that when we take a explicit example.
Just a query, in the papers that we were reading, they had Kruskal thing, right?
Yeah. That's
They,
why
they didn't use any Penrose
They
stuff.
have.
They have used Penrose
Yeah,
stuff.
they have used Penrose.
At the end or something.
Yeah, like pictorially to represent that shock wave.
Oh, okay.
But like since people are like said you can go in detail as well, so I thought okay I'll tell the entire story. Okay. Right. Once I have my metric in this conformally flat form, what I'll do next is consider the zero set of this omega, big omega. So omega t x equal to 0. This is going to be my some set, the zero, which I'll call the zero set of this, and zeros of this. By the way, this r was initially there in the metric, but and when I do the coordinate transformation, this should have been in terms of t and x. But whatever that function will be, I'll just use this coordinate transformation and express it in terms of t. I'm just leaving it in that way. Equal to 0. So this is a set. This is a set. Okay. Yeah. We continue here. I'm just one.
So the first set is omega t x is equal to 0.
Yes. Where basically where this part goes to infinity and this goes to 0.
Okay, you're basically trying to encapsulate all the infinite amount of that TMX in you are shrinking down it
Yeah.
to near part, and you are excluding the spherical symmetry part, and you are also
like this will be incorporated in some way.
in some way. Those are like points that you will draw on the
Yeah.
diagram.
And also one more condition: these coordinates t and x that we have, they should be a part of a compact set. This is a mathematical
Compact in a
integral.
sense.
Compact, like it is a real analysis concept, but like simply the range of either of the coordinates should not be infinite. Simple as that.
They're always finite.
Yeah, we can just take it as a compact. Like we have to define all kinds of things.
But for us, it's a priori.
Yeah, not a priori. Just like for our purposes, it suffices to say, okay, this has some finite range. That's it.
Okay.
Because I said the entire philosophy of these Penrose diagrams is to map an infinitely extended space-time in a finite range. So of course I want my coordinates to be in that finite range.
Okay.
So this is a very important thing. If suppose I do certain coordinate transformation, I get my metric in this form, but then I see, okay, this t and either t or x is running up to infinity. I again have to make some transformation such that I finally bring it into some form such that the coordinates do not have this infinite range. Basically, t and r vary in a compact set. Okay, so once I have this machinery, I have my Penrose diagram straight away. So Penrose diagrams, as I said, so this part being 0 will have a different some curve. It's a 2D equation, right? So of course it will have some. Let's call this as t and this is x. And say, and this r square t will also have something. It will trace out some curve. Now I have drawn a very. It's not like a generic picture. It might as well happen in some cases that there are no elements in this r square. Like in this set, all the contribution is this from this set. Even if you have just contributions from this 0 set, we'll draw all the curves out in this 2D plane that will constitute it to a Penrose diagram. Okay, maybe
It's just hard time understanding how that green part is being drawn.
it's basically suppose this sigma t is simply t square plus x square
Okay.
equal to 0. All x and t that follow this equation, they will trace out some locus in this 2D plane.
Oh, you're just drawing a rough picture.
Yeah, it could be anything.
Okay, it could be anything. So okay. For those kind of equations, you are just
Yeah.
green part refers to that equation.
Yeah, that locus.
Is this necessary? They should be connected like both.
There will be specific examples. It will vary from example to example. Like I said, in the case of Schwarzschild, there will be one regime that will be inside the horizon, the interior region, exterior region, where there will be no t and x satisfying this equation. There will be only these, and they will form a closed square. So, like generally, this types of space-times we deal with, they have this natural property that when you draw these Penrose diagrams, they are always going to be closed somehow.
So basically, we have to draw these two equations on this t or tx space.
Yeah, like this is 0, this is 0, draw the curve, and your Penrose diagram is this.
The shaded part.
Shaded region inside.
Okay, the
We
part
could have taken outside as well.
outside as well.
Yeah, but the philosophy is, again, I want everything, all of my space-time information in a finite region. And while taking explicit examples, we will prove it. Like all the infinite coordinates get mapped to just one finite region.
Okay.
This is a very abstract definition of Penrose diagram. Like I found it to be really interesting because no one has taken this approach.
Yeah.
So like this in a way becomes a recipe, right? We can take any space-time now. Just that if I have a 5-dimensional metric, suppose R space-time, and let's say B equal to 0, because these Penrose diagrams are for spherical symmetry.
They have three sphere.
Yeah, exactly. The topology will just simply change. Like now I have some, let's say S3 cross R. All I'm caring about is this T and R part, the interplay, the causal structure. So we can very well draw a Penrose diagram for our space time.
As for real.
Yeah, R real. Just that now every point in our 5-dimensional metric would, instead of a 2-sphere, represent a 3-sphere. Topology changes.
Again, jumping ahead, suppose if we had some crazy complex notions, instead of R we had C's, then how could we have like drawn
I don't
But
think
yeah,
complex numbers, no. I don't think complex numbers.
instead of S cube cross R, we have X cube cross C cross C.
No, then it effectively becomes 4 real dimensions.
Yeah.
C cross C is
We
2
don't
complex
draw
dimensions.
them. We draw their modular surface or something.
No, I don't.
But
they
okay,
will
that's some just wild imagination from my side. Okay, let's go back. Let's get back to.
Like if you want to go into the regime, like a complexified Minkowski space, twistor theory again deals with that.
Yeah, okay.
That's why.
yeah, okay. I'll read it in my spare time. Let's get back to the Penrose.
Yeah.
Can you explain how this contain entire like information
Okay.
causal structure?
This is an information-based thing. Like, of course, there would be very rigorous mathematical proof of this. Like mathematicians would have figured out. But as physicists, I think once I give an example of the Schwarzschild spacetime, everything will be clear. How everything is getting mapped inside a finite region. I think we should.
This is just a rough algorithm.
Algorithm, yeah.
Okay.
We could just take it as an algorithm.
Okay. And then you are going to give us some examples using
Yeah,
this.
Schwarzschild, like the beautiful diagram that you would have already seen, 2 black holes getting connected by Einstein-Rosen bridge. That will get beautifully
By this Penrose type.
Penrose diagrams. Yes.
Okay.
Kruskal found it by doing a coordinate construction, but Penrose diagrams are powerful. You do not have to do any coordinate construction or think about it. You just have Penrose diagrams in various regions. You have to very smartly glue. Smartly glue. There are rules for gluing. I'll say what those rules are. There are very obvious rules like time orientability and everything.
There are like topological rules, like you have to.
No, causal rules.
Causal.
Simple causal rules. That will become more clear than I draw.
Okay.
For
So like topology needs to be preserved, something.
Time, the orientation of time needs to be preserved.
Orientation of time.
Yeah.
Okay. Yeah. Okay. So you're going to give us the examples now.
Yeah.
This is the algorithm now.
This is the algorithm, the most general way. Okay, so one more advantage of this Penrose diagrams, like why people care about these Penrose diagrams.
I think you have to use that next.
Okay, so there is one very interesting property of these Penrose-Carter diagrams. Like I will draw a very general figure that I have just drawn. So suppose this is my curve. Note that I am drawing a finite curve because I initially did ensure that my t and x are varying in a compact set.
Okay.
It could have stretched to infinity, but then there is no point of drawing these Penrose diagrams. Okay, so this was where my omega was 0, and this is where my r square was 0. I said the interior region is going to be my Penrose diagrams. Now, now we had this metric of this form 1 by omega tx minus dt square plus dx square plus the spherical symmetric part, which I don't care about. Now, in like the beauty of this coordinates is like for null rays we simply have that dx square equal to 0.
Yeah.
So if I just want to deal with the Lorentzian part, all that I'm going to map in, it simply means that dx equal to plus minus dt. Straight lines.
Straight lines.
Exactly. So null rays become straight lines in Penrose diagrams. So yeah, something I'll just draw on black.
At 45 degrees angle.
45 degree angle, yes. So these are going to be my null curves inside my Penrose diagram. And so once, like, why having null like curves as straight lines in your geometry helps? Okay, so one very good aspect of these Penrose diagrams is that since these null rays now are traveling at 45 degrees, like they are straight lines, drawing any causal curve means either space-like, time-like, or these light-like curves itself. So like suppose if you want to draw any time-like curve, we can draw it very simply, like allow time-like curve. Because now we know at each point of this Penrose diagram, we have to make sure that the tangent or the trajectory lies within the light cone. Then it's a time-like. Suppose this is a light cone, and I'm drawing some space-time diagram. At every point, my tangent has to lie within this light cone. That's how you say it's a time-like curve. So I have my light cones ready now already. So this is a light cone where there is an intersection. So this is a light cone.
You can choose anyone.
Yeah, like each point have a light
Yeah,
cone.
we can
Each
choose
point
anyone.
has a light cone. So this is a light cone. Let's say this is
How
a
will
light
you
cone.
decide in which light cone to travel, or it will travel?
It can travel any, like a time-like curve. Like now you can very simply without doing any calculations, you can just trace out a curve and you can say, okay, this is time-like because at each point, it is the tangent vector is lying within the light cone. It could be anything, any curve that we want.
I think it will be clear by examples.
Yeah.
The idea can get clear by examples.
Yeah.
Because right now it's a rough curve, rough sketch.
No, like this thing that I'm saying, that this curve, these boundary sketches are extremely random. Of course, most of the times you're going to have this nice rhombus kind of shape, but okay. This notion is very precise because whatever may be the shape of the boundary, inside these are at 45-degree angles.
Yeah.
So I can draw any curve that joins these points, and that's going to be a time-like curve or a causal curve. So this is my causal curve. I'm just going to keep joining these lines. Yeah. So this is my causal curve. This is another one of my causal curves.
Like time.
Both
No. This is space-like. This is space-like. Sorry, this is space-like. This now, yeah, this lies outside my light cone. Suppose this is a light cone here, and now my light.
That's why I was confused. Like you're trying.
No. Sorry, this is a space-like. Okay, you can take this as a space-like. Example of a space-like. So this is space-like, and this is time-like.
Basically, when you're going like in bottom to up fashion within your light cone, then your time like. If you're at an angle, you cross that light cone. Basically, you are left to right or something. Then
Yes,
it's
space.
space like.
Yeah. So in this diagram, I've taken this. My time orientation is in the upward direction.
Yeah.
Time is increasing in the upward
For-
direction. So light cones are like
Yeah.
this way. Okay. So yeah, so that was a very abstract idea of a Penrose diagram. Now we'll take the most beautiful example.
I'll start with examples.
Yeah,
Okay. Which example are you going to take?
Schwarzschild.
Short shape. Okay,
Yeah.
fine.
We go to Minkowski, but it is not interesting. Like the black hole, the entire black hole thing gets really beautifully. Okay. So, example, a very beautiful example indeed. Schwarzschild space-time. And also, like the real beauty I think comes when you do the Kruskal extension of it, which is what is relevant for us. Okay. So I'll begin with writing down the line element for the Schwarzschild space-time. This is all in natural units, by the way. So plus the spherically split.
CS करना बाय 1 minus 2 नहीं होगा.
Oh, okay, sorry. Okay, so this is my line element for the Schwarzschild space-time. Okay, so first step was to get this metric into that conformally flat form. Consider the zero sets of the conformal factor and the radius, and consider the intersection, and the region subtended inside is going to be
We are applying the algorithm.
Sorry?
Applying the algorithm actually.
Yeah. So now, as I said, like the very natural choice that we do again and again, like to bring it into a conformal form, the first choice is called going to the tortoise coordinates transformation.
Just a question, why they are called tortoise?
I don't know, some maybe.
Because they are spherical.
Surname,
The shell of the tortoise like is.
like isn't it some surname of a scientist who discovered it?
Oh, maybe.
I don't know.
Maybe.
I don't know. I don't
I
know.
also don't have any idea. So Brigham was doing all these tortoise coordinate transformations.
Okay.
I'm not sure. Okay, you can continue.
Okay. So basically, yeah. So if I do my tortoise coordinate transformation, so R is my tortoise coordinate. This is how I will do it. Okay, so as soon as I do this, of course I'm going to get my metric in the form that I desire. Let's see. So we are go square or something. 1 minus 2 and by R is my conformal factor.
Plus कॉर्डिनेट में नेगेटिव साइन नहीं रहता.
Kruskal अच्छा, like we are not like the approach that Kruskal followed. Like he started from the social line element and he kept doing a series of coordinate transformations until what he claimed as a maximal extension. I'm not going to follow that approach. I'm going to follow the approach like I'm going to unleash this power of these Penrose diagrams, like make us realize how can these diagrams be actually useful and powerful to us. Without doing the coordinate transformations that Kruskal did, I'm just going to take a series, precisely 4 Penrose diagrams, glue them according to some causal rules, and I'm going to see that I have generated exactly the same space-time that Kruskal had done after doing a series of coordinate transformations.
Is it a much easier method compared to Kruskal?
Absolutely, you can do it for any like social is still a very simple metric. Like you can keep doing transformations. Suppose I give you any random metric. This is a very
Easy.
like better way, not easy.
Basically, metric is the standard metric. So.
Yeah. So for any general, that's the reason why I thought like it would be helpful to a larger audience, like doing it using a general approach. Okay. Yeah. So minus dt square plus this transformed dr square, which is my tortoise, plus this part that I don't care. I have my form already. Like my omega here is this simply 1 upon 1 minus 2m by r. But I made a condition. I said that the coordinates that I'm going to use, I want them to be finite or compact set to be more mathematically precise. But if I integrate this equation and I find the form of r, I'm going to get r plus 2m logarithmic of mod r minus 2m. This is what I'm going to get. So this is my tortoise coordinate in terms of my old coordinates.
Okay.
R ranges from 0 to infinity. We can very easily see that capital R ranges from minus infinity to plus infinity. And I don't want this. I want my coordinates to vary within a compact set. So this possibility is ruled out. I have to do another transformation which gives me what I desire.
Okay.
So the next coordinate transformation that I'm going to do is generally what turns out, which appears some way or the other in every Penrose diagram we are trying to construct, like be it Nordstrom or Minkowski or the Schwarzschild. So this transformation I think is a key transformation when we are drawing these Penrose diagrams. So following is the set of transformations that I want to do. So I started off with r comma t. Then I did my tortoise coordinate transformation. I went to capital R comma T. Now I'm going to make further transformations and going to U comma T. Or maybe time is better to write time first. I had T comma R, then I went to T comma capital R, then I'm going to now T comma U. These T comma U, which I'm going to just define in a minute, these are going to be finite ranged, and plus they are going to give me this conformally flat form. So following other transformations. So this is small t.
This is sign argument T, right?
Yeah, of course. And so I am in this coordinate. I have written what I want for t, and I will write for r. So this is the main, like the main transformation that appears everywhere.
But how do we choose this?
How do we do this? The underlying motivation should be like my aim is to somehow map all the space-time points in a finite region. So I want my coordinates to be finite ranged.
Okay.
So I have a way suppose in this coordinate system I had r that goes from minus infinity to infinity.
Don't want it.
Okay, so maybe I'll just write it down and then we'll see. Cos t plus u by 2. Like using these trigonometric functions is like the most natural choice comes like sine and cos, because sine and cos take input values right up to infinity and still give you a finite value. Similarly with the tangent function, it takes all the inputs from minus infinity to infinity and gives you a finite output between pi by 2 to minus pi by 2. Similarly tan inverse. So of course these are the
Penrose diagram, I guess they usually take tan.
Yeah, that's the approach that people generally follow. But like this is a very powerful approach, I think. This is an approach that can be used like more generally for several space-times.
The choice of expression has to be such that your R is finite.
Sorry?
Because
Yeah, the coordinates are finite and the metric takes this conformally flat form. These are the two motivations. If you can find a coordinate such that these two conditions are satisfied, that's a good choice.
any coordinate we can find that satisfies it is applicable.
Yeah, because we want first finite range mapping, and second we also want these light rays to go at 45-degree angles. So I necessarily want this conformally flat form.
Okay.
These are the two key aspects of Penrose. So if you can reserve it, that's how that is a good choice. So these are the transformations. Like if I do this and then I substitute back.
Just write the expression after substitution.
Yeah. So this is what my metric will turn out to be. 1 minus 2 m by r. Basically, I will.
What am I?
Okay, fine. Yeah, so this is going to be my metric after the coordinate transformations I do. So cos square t plus u by 2 cos square t minus u by 2. So this is going to be my conformally flat part. So now I have gone into d capital T square plus du square plus 1 minus 2 m by r I think whole square. 2 square. or maybe just
Cross check. You have notes, right?
uh, yeah, this is what.
Okay.
So doing these coordinate transformations, you arrive at this. Now the t and u are in a finite range. I also have in my conformally flat form. So now we are getting very close to the final version of the Penrose diagram. Okay, so that was the coordinate transformation that we saw, and based on that, I'll write down the result that I have for my conformal factor now, which is simply this. Okay, so drawing now the key thing that we have to note here is that in this Schwarzschild metric we have a coordinate singularity at this point, at this radius of r equal to 2m, the Schwarzschild radius. So now when we draw these Penrose diagrams, we are going to draw it for two regions. So there are going to be two separate Penrose diagrams. First, my first region is going to be I think greater than 2m. Okay, let me make this as a second region because that's a little bit subtle. The first region is going to be r greater than 2m. So outside the horizon, between the curvature singularity and the horizon. So there will be two Penrose diagrams. There will be two more when I do a transformation u goes to minus u. So I'm just telling a roadmap by how it will go now. So when I do this transformation, I get two more Penrose diagrams. So in total, I'll have four. I will causally, quote unquote, causally glue these four Penrose diagrams to reproduce my Kruskal extended space-time, globally extended space-time, which Kruskal got by doing coordinate transformations. So that's how. Sorry.
Doing them using some rules.
Yeah, I'll mention the rules. So what we'll do is, I will explain these two regions. After doing this, it will be very simple. We just have to do like axis, like u goes to minus u, so reflection about the t axis. So we'll get four diagrams, and then we'll glue them. Okay. Sorry, it's going lengthy, but I think
here the denominator is still 1 minus 2m by r.
yeah. Now that's the key point. If I would have not made this distinguish, that would have given me a trouble. So now when I'm in, let's say, first region, I've not put an equality sign there. As I said, outside 2m, so this is not going to give me any trouble. I'm outside the horizon. This region, I'm safely inside the horizon. That is why it was necessary to do this division.
I think that stuff is called coordinate singularity in which
Yeah, coordinate singularity. Basically, because when you throw in null rays, it's like if you switch to some other coordinate system, like the Finkelstein, Eddington-Finkelstein, that singularity vanishes. Curvature, because like the Kretschmann scalar blows up, so it's coordinate invariant singularity. Okay, so I have my omega now, and there was a second thing that I had to make zero. That was my, if you remember, r square as a function of tu equal to 0. Right? This was coming from a spherically symmetric coefficient. So these two together would have given will give me the Penrose diagram. Okay, so finding this solution for this is going to be very easy. These are
Gamma tu will also be 0.
sorry.
Omega tu will also be 0.
Yeah, of course, yeah. Like zero set of both these two functions. But for r square equal to 0, we'll need this plot. I think the way it will be worth it because it's really beautiful at the end. Okay, so so now I'm in the regime, this first regime where so basically this plot comes like when I did my initial transformation, the tortoise transformation. I had this integration equation d capital R equal to d small r, and then I integrated. I had got this function 2m plus logarithmic or something. So I've just plotted that.
Okay.
Okay. So now we can see for this r greater than 2m, this r, sorry, this should have been capital R, I guess. Yeah, sorry, capital. No. Okay, small. Yeah, so we can see that for in this regime, like this value is 2m. So at this side, this is this, this is this. So r greater than 2m, we see there is no root for r, the small r. So like I said, this has no values in its zero set, no values, because you can clearly see in regime r less than 2m, I do have a point where r square is 0. But here I don't. So all that I'm going to get is from this region, from the zeros of this.
Then it will be capital R, I guess.
No, that's going to be smaller.
Smaller.
That's going to be smaller. Like we started off with the Schwarzschild line element as like in front of that spherical part it was r square, right? Small r square. I have not changed it throughout. I have just said I'll keep my r square as it is. Whatever coordinates I am choosing, I will just express it as a function of those coordinates. I haven't changed that. Okay, so almost close now to the first Penrose diagram. So the Penrose diagram is going to come from the zeros of this. Okay, so zeros of this are simply like basically when this cos square is either this argument is plus pi by 2 minus pi by 2, that's the closest, like the nearest, like the smallest solution that I can get. Of course I have 3 pi by 2, 7 pi by 2, but like I said, the smallest region that I want to choose is my Penrose diagram in my general description. So when I consider zeros of this conforming factor, these are the 4 equations I'm going to get. Right? Now we're almost there. Okay. So this is my t-axis. This is my u-axis. These lines are simply these lines. Maybe I'll just draw it in bold.
The t, all the t minus u plus pi minus pi and minus u plus.
Yeah, these are the 4 lines that I've plotted, which comes as the zeros of this equation.
Okay. Now connecting that with this.
Sorry?
Now you have to connect that with this.
Yeah. Like I said, like all the space time will be contracted. I have it right. I just want to make it explicit now. Okay. So basically, so this line is t equal to minus u plus pi. This is u plus pi. This is u minus pi, and this is minus u minus pi. These are the 4 lines. now I want to somehow relate the lines that I have got with my initial social coordinates, which had an infinite range, both small r and okay. First maybe first I will go with this tortoise coordinate. Okay, I had this capital R. I can write this capital R as a function of t comma u.
Yeah.
Okay, I'm not doing entire calculations. One can prove that limit as limit r of t comma u when you tend t, suppose I'm talking about this line, I'm going to tend towards this line from the inside, because from the definition I want my region, Penrose diagram region, so I'm going to tend towards this line from inside. So when I do that, when I tend t, suppose this line is minus u plus pi, I get plus infinity. Okay. So basically, so when you calculate the limit from here for this line, limit t tends to u minus u plus pi, I guess. Yeah, whatever, u plus pi, r t comma u. This is also plus infinity. So these lines correspond to r equal to plus infinity, r equal to plus infinity. These lines, okay, so I had this r equal to infinity, which I found by approaching this function of r as a function of t u from this side. For this line I approach from this side, for this line I approach from this side, and this line I approach from this side. So when I calculate these limits, like there will be, this is the first, this is second, third, fourth, like all four lines. This is what I'm going to find. This line corresponds to capital R equal to infinity, also infinity. This is minus infinity, this is minus infinity.
Okay.
Right. So just one step away now.
Mm-hmm.
I'm realizing the Penrose diagram is there.
Okay.
Realizing that now how have we indeed. Now just look at this diagram. We are in this regime,
Yeah.
r greater than 2m. So r goes to infinity. What does it correspond to when in terms of small r?
1 minus 2.
No, like r tends to infinity is the small r goes to infinity, right?
Oh yeah.
It's increasing this way. So r tends to infinity corresponds to, this implies small r goes to infinity. This small r was the initial social coordinate that we started off with. This means this
Goes to infinity. Okay.
this also goes to infinity. And what does r goes to minus infinity correspond to? Simply 2m. Like if you see r goes to minus infinity, it goes to r equal to 2m.
It's like asymptotic.
Yeah,
Asymptotic
yeah.
to that too.
Yeah.
Okay.
So this is small r equal to 2m, small r equal to 2. That's it.
Can't go beyond that because it's there. Yeah.
Yeah, from the graph just.
Okay.
It's going minus infinity, x is going to 2m.
Okay.
There you have it. Like now, I was dealing with this region r greater than 2m. Now I've totally encapsulated my infinite range, which went from 2m to infinity in a finite.
Yeah, bound. It's like boundary.
Bound, yeah, this is bound. So it is bound by 2m and infinity, the two ranges that I had.
Yeah.
So I have shrunk my space-time into this finite piece now.
Yeah.
This is the Penrose diagram.
Okay. It reminds me of the movie Honey, I Shrunk the Kids, but you have just shrunk the whole space time.
Yeah, like it's just a very smart way of mapping. Like we can always map, right?
Yeah.
There are infinite points. I can map it to a finite set somehow, and that's what we have accomplished with this.
And basically, you have had some meeting, you scaled it down to
Yeah.
some smaller notions, and your boundary is at infinity.
Yeah.
So-
Now
and-
I can, like, all my space time is right in front of my eyes. I can do whatever I want.
Yeah, that's a better picture, I think.
Yeah. This is the whole idea of Penrose diagram. So now I'll quickly just get to the Kruskal extension picture. So I gave an example for this regime. So let me just lay it out. We'll finish this quickly. So we had this first region. r greater than 2m, this is the Penrose diagram. Now I'm simply, same calculations you have to follow, just that now we have this capital R goes to infinity, right? In this regime, this capital R going to infinity corresponded to small r going to infinity. But in the regime r less than 2m, there is, it terminates here. So for the regime r less than 2m, this capital R does not take infinity at any value. So of course in this regime, this is not the bound. Something else has to be the bound.
Yeah.
And that bound is going to be provided by this. Because in this regime I did not have this. So only contribution that I got in my Penrose diagram was from the zeros of the conformal factor.
Yeah.
Now in this, like we can see clearly from the diagram, like this is the finite point where this small r goes to 0. It corresponds to 2m ln 2m. So this is a finite point.
Yeah.
Okay. So if you draw draw this curve inside this, you will get something like this. Yeah. All this portion to the right of it goes away. So this corresponds to my small r goes to 0. That's that. Which means my capital R is this value. And I know capital R as a function of t comma u. So now I have a function, like some function, say capital R of t comma u equal to this value r naught. Right? I can plot this in this Penrose diagram. When I plot this, I'm going to get this. So the definition of this Penrose diagram was like the curves. You have curves and you can bound it. Like this is the region now. And rightly so, beyond this, we clearly saw that R, capital R going to infinity cannot be achieved, right? Clearly from this picture.
Yeah.
So that this portion now is my Penrose diagram for this second region.
After that bump, what happens?
After that, we saw, right, we cannot attain these values at all.
Okay.
Like this is the boundary for the second regime.
Yeah.
In the first regime, capital R going to infinity, I could find a value for small r such that capital R is infinity.
Yeah.
But here I cannot. So of course this region is not going to be my, like recall the initial, I said like there will be two curves. I'll have some bounded region. This is exactly what is happening.
Okay.
This is coming from my conformal factor 0 set. This is going to 0. And this is coming from my r square going to 0.
Okay, so the shaded one is the one.
Is a Penrose diagram.
Penrose diagram. Is it shaded just to the right of the origin?
No, like this one. Yeah, this r goes to 0, goes right to.
This is the boundary, and okay.
Yeah.
These two cross, and that
exactly.
is the Penrose diagram.
That's the Penrose
Okay.
for this regime.
Okay.
Okay. So that's what it is. Now I'll quickly finish this more beautiful part.
Stopping it here.
So we saw the Penrose diagrams for the two regimes. So R greater than 2m, that was one regime. R greater than 0, less than 2m, that was the second diagram. Now I'm going to get two more diagrams, which I'll get by doing the transformation u goes to minus u. So simply when I drew my TU diagram, when I do u to minus u, whatever diagram I have, I just symmetrically flip it around the t axis and I get the two diagrams. So doing that, these are my final four diagrams that I'm going to draw. So this is the first diagram. This holds true, by the way, in the regime r greater than 2m. Second diagram. Third diagram, which I have. Okay. So this is my r equal to 2m. r equal to infinity, r equal to infinity. So when I flip this, my infinities are going to come this side, and my 2m go this side. Okay, and the flow diagram, of course, is going to be like this.
Reflection of that.
Yeah. Okay. So these are my 4 diagrams there again. Now I want to glue them.
Glue them.
Yeah. So I will be following. Okay. There was one more thing: time orientability. Simple thing. When I had this conformal factor, I had an expression for it. Depending on the like, if you remember, I had like something in the numerator, and I had 1 minus 2 m by r in the denominator. Right. This was the form I had. So for the regime r greater than 2m, omega is greater than 0. For the regime r less than 0, it's less than 0. Right. Simply from this term here. Okay. So when omega is greater than 0, my time orientability is of course in the
Positive.
plus t direction. If my omega is less than 0, then my u becomes like behaves like time, right? Because this is what
Interchange happens.
Yeah, exactly. So if I have some positive quantity outside, so my time like behavior is in this t coordinate. If this becomes negative, this negative goes inside this, it makes this positive and this negative, so my time orientability goes in u direction, right? So for this diagram, time orientability is in this direction. For this diagram, time orientability is in this u direction. For this diagram, the time orientability doesn't change because I've just switched u to minus u. It does not change the metric because it is du square. And for here, the time orientability
Left.
left, yeah, it goes to left. Right? So this is what I have. Yeah, this is what for R and likewise for the others. Now I want to glue them. So I have rules. When I like, these are representations of different sections of space-time. Okay. So when I want to construct a global space-time, like when I'm gluing them, I'm not doing some like trivial geometrical stuff. I'm bringing different pieces of space-time together. Okay. So my rules are going to be, first, any space-time is always time orientable, right? It is not like in certain space-time you'll have time ticking along some one direction, and in another part of the space-time it's another direction. So I have to keep my time orientability always same. So what I do when I glue these diagrams, okay, I have this as up, this as up. So I'll take it as a convention. Okay, I want for my space-time time orientability to be up. So these diagrams will be a problem. So what I'll do, I'll just rotate them such that my time orientability is in the upward direction.
You rotate one counterclockwise and one clockwise.
Yeah, so time orientability preserved.
Okay.
Okay. Second, where like I will have these r equal to 2m's everywhere, right? I have
So they are on the same side.
Yeah, right. So this corresponds to r equal to 2m, r equal to 2m. This corresponds to r equal to 0. This corresponds to r equal to 2. Oh, sorry, that's it. Sorry. R equal to 2m, r equal to 2m, r equal to 0. Okay. So when I have to glue r equal to 2m
like
surfaces.
common.
Yeah. Surfaces or whatever lines.
It's like where r at is equal to 2m, just
they have to join because of course it has to be consistent, right?
Yeah.
And third, I cannot glue r equal to 0 and r equal to infinity for obvious reasons. This is a curvature singularity. This is my asymptotic boundary. Of course, I cannot glue these two.
Yeah.
So I always have to keep them at the boundaries. Okay, so we have these 3 rules. We have all the 4 diagrams. Now I'm going to build what we call as a maximal extension, and I'll explain why a maximal extension. So if we follow the rules, this is what we'll get. Right? So
Yeah, okay, and one more, yeah.
okay, so all these are r equal to 2m, 2m, r equal to 2m,
and r is equal to 2m. We have our
Penrose.
Penrose
r equal to 0,
R equal to 0.
coordinate singularities,
infinity.
and this is the asymptotic boundary. So preserving all these rules, this is the diagram that you
Preserving all these rules, we have our Penrose Rangoli. Okay.
Okay. So now when I take these four pieces together, you could say, okay, I could have done some other like transformation, and I would have another Penrose diagram. I could have glued it and extended further. But now you can see, like at these boundaries, all I have is 0, infinity, 0, infinity, 0, infinity, and we had this rule that we cannot glue these.
Mhm.
We have, like, had there been some 2m floating around, maybe we could have extended further, but that's why this is called as the maximal extension. You cannot extend your space-time beyond
Beyond
this.
it. Okay.
Okay. Now some very interesting properties, like what is this physically even telling me? Okay. So this. Okay. So let me number these regions. Typically, people do number these regions. Okay. So very interesting now. I said in the Penrose diagrams, the best thing we could do is like one of the nicest things we could do is like draw these 45-degree lines and then draw the causal curve, which becomes very easy. Now suppose I have some observer who is starting from here, like asymptotic boundary, and now it is traveling in the upward direction, let's say. So as soon as it crosses this horizon, there is no other way for this particle to go, like anywhere to go. It necessarily has to just go and collapse into the singularity. Why? Because, like, suppose I say, okay, I have gotten inside this, now I can take some curve this way, but that will violate, because that is a space-like curve, right? I had shown an example when I drew the most generic example, like if I have this horizontal, yes, and my time orientability is in upward direction in this diagram, as I said. So when I go along this, I will have my tangent vectors outside the light cone. So this, any path which goes along this will be my space-like part.
It will break causality.
Yeah, so that cannot happen.
No.
So so the power of the Penrose diagram, you did not have to do any mathematics. You just simply draw a curve, just take it beyond this 2m, and you directly have the conclusion that it cannot escape the horizon now. Just on the basis of the causality. So that's one power. Next, so based on this observation, people call this one as the exterior region and 4 as the interior region. Why exterior? Because once the particle comes from this and it crosses this region of 2m and enters into this region 4, it cannot escape. So that's why this is the exterior, this is the interior.
That's basically the horizon. Once it's inside the horizon, it will go.
Yeah, like generally what we do is, like, suppose we are in a Schwarzschild space-time, what we do is we consider null geodesics crossing the horizon, and then we have to prove by doing manipulations that, okay, now this null geodesic cannot escape the horizon. We have to do mathematically, but this Penrose diagram is directly revealing.
Graphically telling it.
Yeah, it's pictorial.
Yeah, pictorial.
Second very interesting thing. Suppose my particle starts from here.
Singularity.
Yeah, suppose, okay, not singularity, maybe inside here, somewhere inside here.
Inside a black hole.
Yeah, inside, like inside horizon, suppose. This particle can escape outside.
Wait.
This is a strange thing. This is a particle, it is not violating, it is following a perfectly timed curve here.
It's like Hawking radiation.
No. Nothing to do with Hawking radiation. Like,
I'm
this
not
is
getting it. Like it is inside the horizon.
that's the point. Like, when we say that particle goes inside the horizon and it cannot come outside, it holds true when you are dealing with just one black hole. You have one black hole, you have just one exterior, or from that exterior crossing the horizon, and you cannot come back.
Are you talking about white hole?
Exactly. Wormhole. Yeah, wormhole.
White
Exactly
holes are.
follows from here.
Okay.
Yeah, now this is where it gets interesting. So there is some region like beyond the horizon, a particle can come outside, cross this horizon and come into the exterior of this space-time.
Okay.
Right?
But that's not a black hole horizon. That's a wormhole horizon.
No. Wormhole doesn't have horizon. It's like
How to explain this? Like
it's like suppose you have these two black holes. They are connected by this Einstein-Rosen bridges, right? Suppose this is the horizon of this black hole. When you are dealing with only this black hole, like when you shoot in a particle inside, like if you have a particle inside the horizon, it cannot escape outside. But of that same black hole, the particle inside the horizon of one black hole can escape into the exterior of the other black hole. This is what this diagram suggests.
because they are both connected.
Yeah, via this wormhole.
Okay.
In this picture, if you can guess this point here, just one point, this is the wormhole or the Einstein-Rosen bridge. It is a point in this diagram, but it is a two-sphere.
Two black holes connected by an ER, Einstein-Rosen bridge. Which
Exactly.
is basically a wormhole. Okay.
Yeah.
Okay. Yeah.
It comes directly from this diagram. You can see it beautifully, right? So, just based on these observations, you call this region one as
Exterior, 4 is interior.
yeah.
What about 2 and 3?
Yeah, like the one is okay. So this also is exterior. Okay, maybe I'll keep the color code same. So 1, 4, 3, and 2. Okay. So 2 is also exterior. This is an interior, but this is a past interior. This is a future interior. This is the right exterior. This is the left exterior.
Can you explain the notion of left and right?
Simply based on the diagram. This is right side. This is left side.
Okay.
Here it is like
Light cones.
coming.
Light.
Yeah.
Like it's in the past, so it's past
Yeah,
interior.
it's time orientability is in upward
Ah.
direction, so it's emerging from the past and coming into the future.
Okay. Yeah. Okay.
And here we say when we say it's future interior, it means from this it's going towards the future
Okay.
because time orientability, because of the time orientability. So
So-
that's it. This is the critical extension, which is relevant, and we'll carry on from this in the next one. So like this critical extension will be necessary to do the shockwave analysis.
Okay.
So that's it.